Harmonic Vibration Feedback System project with Navier. Our objective was to design a system that integrates into a milling machine and measures and records the natural frequency of a workpiece. Our end goal became to create a system that can measure the harmonic frequencies of any part and display the desired spindle speeds and feed rates that will avoid exciting the part's natural frequencies. The milling of thin-walled parts often generates significant vibrations in the workpiece, which cause chatter. This forces the machinist to reduce material removal rate until chatter stops. In order to avoid the frequencies which cause chatter, it is necessary to determine the natural frequencies of the cutting tool and the workpiece as geometry changes during the milling process.
Specifications. Device must not alter part harmonics, and it must not interfere in machine's operations. The accelerometer must attach in a non-destructive way and must have low sensitivity in which to capture higher frequency.
ANSYS was used to calculate the natural frequencies of the rough part before it undergoes the finishing processes. The frequencies are listed below. The following table shows the theoretical versus the experimental resonant frequencies gathered on the part machined by the team. The FRF LabVIEW program was used. While at the Navier facility, the team conducted test cuts using a CNC milling machine and the FFT LabVIEW code. The following table shows vibration data gathered from multiple test cuts at varying spindle speeds with a constant feed rate. Test cut 3 was performed at a previously identified resonant frequency, where chatter was expected. The resulting vibration amplitude was greatly increased, and an increase in chatter was audible. The accelerometer and impact hammer output vibration data to the signal conditioner. The signal conditioner then transfers the data to the LabVIEW program. The LabVIEW program creates a frequency response function from the data. Accelerometer position on the workpiece should be placed on the area of most significant vibration. Coolant jets should be disabled. On the cutting tool, accelerometer should be placed securely on the free end of the tool. Gathering data for the stability lobe diagram requires impacts in the both X and Y direction. Stability lobe diagram created for cutting tools which have a long stick out can be unreliable. Components: accelerometer, impact hammer, signal conditioner, high-speed end mill, petrowax, and part.
The LabVIEW FRF graph displays the resonant frequencies of the workpiece along with the corresponding spindle speeds of each. A machinist can use this data to find spindle speeds that must be avoided. The impact graphs show a live view of the impact hammer and accelerometer readings. The FFT graph shows the amplitude of vibration the workpiece experiences at different frequencies during the machining process. The operator will then have an understanding for what frequencies are being excited. The operator can then adjust machining parameters and measure the difference in vibration amplitude. While the frequency response function and fast Fourier transform programs provide data for the workpiece, the stability lobe diagram gives vibration data for the cutting tool itself. A curve is produced which generates the boundary between stable and unstable machining. Combinations of spindle speed and depth of cut which fall below the curve are theoretically stable machining. This graph allows the machinist to optimize material removal rate while maintaining stable machining.